change with the Newton's cooling law or heating law. So let's remind you what it was. It was Newton's cooling, heating law. So we got to the differential equation and we got to the following expression. This expression means the following. So T is the temperature at any time T of a body that we are studying. Tm is the temperature of the surrounding background. And T0 was the initial temperature of the body. So basically, what this law tells us is that we can get the instantaneous temperature at any time of a body that is put into background, that it's at different temperature. Okay, that in principle, the temperature of the background is different from the initial temperature of the body. So there's going to be an effect if you put a body into an ambience that is at different temperature. This body is going to be either cooling or heating. And that depends basically in the concept of integration R. Okay, so this parameter tells us that if R is less than 0, we will have cooling. And if R is greater than 0, we will have heating. So basically, the body is going to change the temperature accommodating to the surrounding temperature of the atmosphere in which we are at. So let's apply this law to a specific example. So let's imagine that we have a body that is at a temperature that is 70 Celsius degrees. And we're going to put it in a surrounding background that is at 40 degrees. So according to our notation, that is Tm. And it's at 40 Celsius degrees. And it tells us that 3 minutes after, let's put here example. So it tells us that 3 minutes after, the temperature of the body is 60. T at a certain time will be 60 degrees. So it asks two questions. One is that what is the temperature of the body 5 minutes later? So, sorry. What's the temperature of the body 5 minutes later in second? How long does it take so the body can reach 50 degrees? So how long takes the body to reach 50 degrees? Okay, so bearing this in mind, we have several conditions. So let's apply. So again, this is our law. And we know that the temperature outside is 40 degrees. We know the initial temperature of our body, that is 70. And we put it in a median that is 40, okay. And we know that after 3 minutes, the temperature of the body will be 60 degrees. So basically means that the temperature after 3 minutes, it's going to be 60 when the time that has passed is exactly 3 minutes. So here, what we can retrieve is the constant of what we can retrieve is the constant R, okay? So see, the 60 is 40 plus 30 times E3R. So that means that 20 is 30 times E3R. And from here we have like 2/3 is E times 3R. I'm taking logarithms. We have the 3R is going to be the Neperian logarithm of 2/3. So from here we have R, which is 1/3 of logarithm of 2/3. Okay, if you compute this, this is approximately 0.13 negative. I put commas because I'm European, but you can put a point if you are watching this from the United States. Okay, so I just wanted to clarify that. So what happens that R is negative? What does this mean? Does mean that our body is cooling. Isn't it happening? Because we said that our body in the initial time, it was at 70 in initial time. And now we have reached 60 degrees after 3 minutes. Okay, so the most expected thing for us would be that actually the body is going to be cooling. So we're expecting an R that will be negative. So far, so good. So now that we have R, we can respond to questions that they are asking us. Now remember, the first question was, what's the temperature of the body 5 minutes later? So basically, it's asking us to compute the temperature in 5 minutes, given the initial temperature of the surrounded background was T0 minus Tm, and this exponential RT. Okay, so now this time that we're looking for in 5 minutes will be the temperature outside that we said that it was 40 plus the difference in temperature between the initial temperature that was 70 and 40, that is the temperature outside, and the exponential of R that we already have it is 1/3 of this logarithm times T, which is 5 in this case. It says 5 minutes. So well, if we do that and we just compute what it is, it's approximately 55 degrees. So basically it's cooling again, as you can see, from 70 to 55 in 5 minutes. So this was the first question. The second question that asks us is how long does it take for the body to reach 50 degrees? Well, we want to reach 50 degrees. That's the final temperature of the body. And we have the rest of parameters, but we now have to calculate the time. Okay, in which the temperature is that. So basically it would be 10 equals 30 times the exponential and time. So basically 1/3 would be this exponential. And we can just take logarithm. So logarithm of this would be 1/3 or logarithm with the t. So the time at which the temperature is 50 degrees will be basically 3 times the logarithm of 1/3 divided by logarithm of 2/3. And this will be in minutes. So basically you could do the same application with a body that is actually heating up. So with the initial data that they will give you, you will come up with an R that is going to be positive, and that's going to be the difference. So basically, I just wanted to show you a very simple application of the Newton's heating law. And if you have any questions in the comments, you can leave any question for me. Thank you.